Welcome to part 2 of section 2.4 on prime factors and the greatest common divisor. We are using the text Elements of Modern Algebra by Gilbert and Gilbert. This is Dr. Gilbert Eyabi. Subsection 2.4.4 definition. We say that two integers a and b are relatively prime if their greatest common divisor is 1. i.e., in more mathematical notation, we say that a and b are relatively prime. Of course, a and b are integers if and only if ab equals 1. That is, their GCD is 1. Subsection 2.4.5 theorem. If a and b are relatively prime and a divides b times c, then a divides c. The relative primeness of a and b is very important in this theorem. Observe that 4 divides 2 times 2, but 4 does not divide 2. So this is only possible if a and b are relatively prime. Let's go ahead and prove this theorem. Proof. Suppose a and b are relatively prime and a divides b times c. Required to prove. We want to prove that a divides c, i.e., we want to show that there exists an integer k such that c equals a times k. But the GCD of a and b equals 1 implies that there exists mn in z such that am plus bn equals 1, i.e. 1 can be written as a linear combination of a and b. Call that equation 1. Also, a divides b times c implies there exists an integer k1 such that bc equals a times k1. Call that equation 2. Remember our goal. We want to prove that c equals ak. So multiply equation 1 by c and we have acm plus bcn equals c. Call that equation 3. Now substitute equation 2 into equation 3 and we have acm plus ak1n, and that is equal to c. Factorize out a from the left hand side and we have a into cm plus k1n equals c. Now set cm plus k1n to be k wiggle, and that is an integer because the sum of two integers is an integer and the product of two integers is an integer. So we have a k wiggle equals c, and that simply means a divides c, and we are done. Again, if a and b are relatively prime and a divides b times c, then a must divide c. We shall use this theorem to prove another theorem that comes up really soon. So do not forget this theorem. Subsection 2.4.6 definition. An integer p is a prime integer if p is greater than 1 and the only divisors of p are plus and minus 1, plus and minus p, i.e. p prime implies 1. P is greater than 1. 2. An integer a divides p if and only if a equals plus or minus 1 or a equals plus or minus p. So 1 is not prime. The smallest prime number is 2, and 2 is the only prime number that is even. Subsection 2.4.7 Euclid's lemma. If p is a prime number and p divides a times b, then p divides a or p divides b. Interesting. If P divides A times B, then P divides A or P divides B. Proof. Suppose P divides A times B and P is prime. We are required to prove that P divides A or P divides B. If P divides A, then we're done. Suppose P does not divide A, then we have to show that P divides B. Now, recall that P is prime. So if P does not divide A, then the GCD of A and P is 1. And that is because the only positive divisors of P are 1 and P. So, by theorem 2.4.5 above, since A and P are relatively prime and P divides AB, we must have that P divides B. Recall theorem 2.4.5. It says if A and B are relatively prime and A divides B times C, then A divides C. So once more, Euclid's lemma states that if P is prime and P divides A times B, then P would have to divide A or P would have to divide B. This is a very important theorem and we shall use it very often in proofs. Here is a quick problem for you to play with as we continue our lecture. Suppose A divides C and B divides C and A and B are relatively prime. Prove that A times B divides C. It's a very easy proof, so I'm going to leave that as a simple exercise for serious students. Subsection 2.4.8 corollary to Euclid's lemma. If P is prime and P divides the product of n integers a1 right up to an, then P must divide at least one of the aj's for some j between 1 and n. Subsection 2.4.9. We now move to a very important theorem in abstract algebra. The theorem is known as the fundamental theorem of arithmetic or the unique factorization theorem. Statement of the theorem. Every positive integer n is either 1 or can be expressed as a product of prime integers, and this factorization is unique except for the order of the factors. In more mathematical notation, we say that for every a in Z plus, a equals 1, or there exist primes P1, P2 right up to Pk such that I can write a as a product of these primes raised to their respective exponents. And this factorization is unique except for the order of the primes. A quick example. 20 can be written as 2 raised to the power 2 times 5 raised to the power 1. 20 is a positive integer. It is not 1, and therefore we can find primes 2 and 5. So I can write 20 as 2 raised to the power 2 times 5 raised to the power 1. This expression of a positive integer is very important and will be useful to provide an alternative way of finding the GCD and the LCM of two positive integers. Proof of the theorem. I will leave these as a simple reading assignment, and you can find these on page 95 of your text, Elements of Modern Algebra by Gilbert and Gilbert. Subsection 2.4.10 Euclid's Theorem on Primes. Very simple, eloquently stated theorem. There are infinitely many primes. That's all. there are infinitely many primes. Proof. The idea of the proof would be to assume, on the contrary, that there are finitely many primes and list out all the primes, P1 to Pn, and then show that we can find another prime that is outside of these existing primes. And that would be enough for the proof of this theorem. Assume, on the contrary, that there are finitely many primes, namely P1 right up to Pn. These are all the primes that exist. Now, define the positive integer m by m equals the product of all the existing primes plus 1. Then, of course, m is strictly greater than 1 because all the primes are positive and we add 1 to it, and definitely that is greater than 1. By the fundamental theorem of arithmetic, since m is greater than 1, m is either a prime number or m has a prime factor, q. Our goal now would be to show that q is not one of those originally listed primes P1 to Pn. Claim, q is not one of the primes P1 right up to Pn. So we're going to go ahead and have a little proof embedded in our major proof, and we call that the proof of our claim. Suppose, on the contrary, q were one of the primes P1 right up to Pn, then that means q divides the product of those primes because it is one of them. Now, if m is a prime number q, then q divides m because m divides itself. Or if q is a factor of m, then q divides m. So in either case, q divides m. Q divides the product of the primes P1 to Pn, and q divides m. Interesting. Now recall that we defined m as the product of the existing primes P1 to Pn plus 1. Now that implies m minus P1 times P2 right up to Pn equals 1. But if q divides m and q divides the product of these primes, then q must divide their difference. And you can verify that very quickly. Go ahead and quickly verify that if A divides B and A divides C, then A divides B plus or minus C. But what is m minus the product of the existing primes P1 to Pn? It's 1. So that means q divides 1. But this is a contradiction because q is a prime number, and by the definition of a prime number, q is bigger than 1. Q cannot be bigger than 1 and divides 1 at the same time. This contradiction arises from our assumption that q was one of the primes P1 right up to Pn. Therefore, we can conclude that q is not one of the primes P1 up to Pn, and this proves our claim. Therefore, there are more than n primes, and this contradiction establishes the theorem. And we are done. There are infinitely many primes. Before we conclude this section, it is important to give you a formal definition of the LCM of two integers a and b. We have already given you the formal definition of the GCD of two integers, so it makes sense to do that also for the LCM. Let a and b be integers where a is different from 0 and b is different from 0. Then we say that the integer m is the LCM of a and b, that is the least common multiple, if the following hold. Number 1, m is an element in Z+. Number 2, a divides m and b divides m. Number 3, if there exists an integer c such that a divides c and b divides c, then m also divides c. Just like the case of GCD, if I ask you to prove that the LCM of two integers is a given integer m, these are the 3 conditions you are supposed to verify. Here is some bonus material for us. Suppose a and b are positive integers. By the fundamental theorem of arithmetic, or the unique factorization theorem, there exist primes p1, p2 right up to pn such that a equals p1 raised to the power a1 times p2 raised to the power a2 times pn raised to the power an. And b can also be written as p1 raised to the power b1 times p2 raised to the power b2 times pn raised to the power bn. The GCD of a and b is defined as the product of p1 raised to the minimum of a1 and b1 times p2 raised to the minimum of a2 and b2 times p3 raised to the minimum of a3 and b3 times pn raised to the minimum of an and bn. While on the other hand, the LCM of a and b is defined as p1 raised to the maximum between a1 and b1 times p2 raised to the maximum between a2 and b2 times pn raised to the maximum between an and bn. Let me give you a quick example so that this concept can sink in quickly. Example, we can write 20 as 2 to the 2 times 5 to the 1, and we know how to do this from elementary school. We can write 138 as 2 to the 1 times 3 to the 1 times 23 to the 1. Again, we know how to do this from elementary school. Now, we're going to go ahead and find the GCD of 20 and 138 and also the LCM using the fundamental theorem of arithmetic. Now, watch this very carefully. The primes involved in 20 are 2 and 5. The primes involved in 138 are 2, 3, and 23. I'm going to take these two expressions to the saloon and give them a facelift. Let me start with 20. 20 is 2 times 2. It doesn't have the prime 3, but I can insert the prime 3 and raise it to the power 0. It has the prime 5, so 5 to the 1. It doesn't have the prime 23, so I can insert 23 and raise it to the power 0. This is my P1, this is my P2, that is my P3, and that's my P4. What about 138? 2 raised to the power 1 times 3 raised to the power 1. It doesn't have the prime 5, but I can insert it and raise it to the power 0 because a raised to the 0 is 1, where a is non-zero. 23 raised to the power 1. Again, P1, P2, P3, P4. That is why in my expression of A and B, the primes are the same. P1, P2 up to Pn, P1, P2 up to Pn, and the difference comes with the exponent. So the LCM of 20 and 138 would be the first prime 2 raised to the power, what is the maximum between 2 and 1? It's 2. Times 3, what is the maximum between 0 and 1? It's 1. Times 5 raised to the power, what is the maximum between 1 and 0? It's 1. Times 23 raised to the power, the maximum of 0 and 1 is 1. And that gives us 1380. What about the GCD? The GCD would be 2 raised to the power, the minimum between 2 and 1 is 1 times 3 raised to the minimum between 0 and 1, which is 0, times 5 raised to the minimum between 1 and 0, which is 0, times 23 raised to the minimum between 0 and 1, which is 0. So we end up with the GCD being equal to 2 raised to the power 1 times 3 raised to the power 0 times 5 raised to the power 0 times 23 raised to the power 0, and that equals 2. So this is an alternative way of finding the LCM and the GCD of two positive integers A and B. And this brings us to the end of section 2.4 on prime factors and the greatest common divisor. Thank you and God bless you.